Okay, thank you all for coming. I'm going to be giving a brief overview of what our project was before we get more into the specifics. So we were looking at albedo. Now what albedo is basically the measure of how much sunlight is reflected off of a particular substance. Now this is important because of climate change right now, right? When we have all the solar radiation coming in, that's heating the earth. And if we're able to reflect that off, that's actually beneficial. Now what we were looking at was hurricanes, because hurricanes create a lot of cloud cover, and clouds are white, and white objects have more albedo, they reflect more things. So this might be able to create a self-regulating cycle, and that's what we were trying to examine. So we looked at data from those satellites, specifically solar flux data from the CIRS instruments, and what we were able to find was a support for the consensus regarding cloud cover. However, we found some particularly interesting results in terms of timing and a couple other variables which my teammates will get more into.
So Earth's albedo is basically just its solar reflectance, or the amount of energy that it scatters back into space. And this has proven to affect both the energy balance and climate on Earth. There are two instruments that scientists use to measure Earth's albedo. The first is the Ceres, and this measures the perpendicular light that Earth reflects. The second is the Earthshine project, and Earthshine is basically just the light that is reflected from the day side of the Earth onto the dark side of the moon. And this measures wide-angle light. And through using both of these instruments, scientists have been able to determine that the Earth is absorbing more sunlight, which contributes to global warming.
The increased temperatures mean that there's increased rate of ocean evaporation and atmospheric temperatures. At higher temperatures, the rate of ocean evaporation also increases, meaning that more energy is transferred from ocean to the air. At higher temperatures, the rate of ocean evaporation also increases, causing since there's now more moist air being transferred, we observe an increase in cloud formation and an overall increase in low-lying cloud cover. Clouds usually have a higher albedo than the surface below them, and as shown in this diagram, in contrast to high clouds which trap more heat, low-lying clouds reflect more sunlight, allowing to cool the Earth's surface. The nature of low-lying clouds as higher reflectors is because the changes in short reflexes or visible light from the sun and changes in long reflexes or infrared light combine to form a larger value of radiation rather than cancel each other out with other cloud sources. As such, the Earth's overall albedo thus increases, allowing both atmospheric temperatures and water surface temperatures to decrease, and we observe a self-regulating effect on global warming.
To collect data on cloud cover, we use the Geostationary Observational Environmental Satellite, which is also called GOES. And this image here on the left is just an example of some data that we have captured from GOES. And from GOES, we use the band 13 cloud cover measurements, which captures light at a 10.3 micrometer wavelength. We chose that specific wavelength because it's less sensitive to water vapor absorptions, which both improves atmospheric moisture collections, aids in identifying and classifying cloud particles and other atmospheric features, and allows for more accurate measurements at nighttime. So we downloaded data for multiple North Atlantic hurricanes from the year 2000 to 2015, with a period of data spanning from 7 days before the hurricane to 7 days after the hurricane.
So although GOES gave us a lot of good data, we did notice some accuracy issues. So as you can see over here, this is a normal visualization, nothing out of the ordinary. In this case, lower pixel values or white pixels are clouds, higher pixel values or blue pixels is water. However, if we go on to the next slide, we can see various hot pixels circled in red. Now, hot pixels are basically individual values that are corrupted and extremely high for no reason. You can see that they're blue. So in order to effectively smooth out this data and reduce skew, what we did is that we applied a medium filter onto different regions with different individual values.
Alright, so now that we've done data correction, we are now left with a single file.cf file with a bunch of 2D arrays or snapshots over the course of a hurricane. So we call these a collection of snapshots a flipbook. And this is kind of what it looks like. You can see an animation, in this case this is Hurricane Sandy. So how did we make the flipbook? In order to make the flipbook, we use a nested for loop to calculate the percent of cloud pixels for each snapshot line by line, column by column, but we only counted the values below a certain threshold. And in this case, our threshold was 10,000 satellite counts. So to decide what the threshold was going to be, we picked it using Panoply graphs, which is a software made by NASA, and we saw the outliers with the software objectively. So a base value was decided based on previous data from several different hurricanes, such as Sandy, Ingrid, Sean, and many others over the course of the past 20 years. So we noticed that a plus or minus 25% change in the threshold value did not really affect the graphs due to our hot pixel correction, so the outliers were only in both the high extremity and the low extremity. So our next steps is we plotted the percent cloud cover versus time over the course of various hurricanes. On the right here, you can actually see the Hurricane Sandy graph for our cloud pixels. And later on, we will do a superposed epoch analysis, which corrects for any errors during this process.
So now that we have the cloud coverage data, we actually need to gather the albedo averages to see the trend. We use NASA's ELX series instruments to measure the data. Not those ones, obviously, these ones. And even though we got albedo averages from those instruments, we didn't really like them, so we decided to calculate them on our own because we're really smart. We ordered data products from NASA Logics ordering system, and we collected hourly data for this specific region of the North Atlantic, and we calculated the albedo from it. And it's a really simple formula, the shortwave flux over solar flux value, and it gives us albedo, so yay. But unfortunately, all the values that we got were ones and zeros, and there were way too many zeros, and nobody likes zeros, especially on tests. So we decided to conveniently sweep them under the rug because guess what? They were nighttime data. And in the night when there's no sun, there's no reflections of sun rays. So you know what? They can go. And now we have, again, a bunch of flip-book images. And they look kind of like this. And if you compare it back to the cloud coverage data, whoa, they look so similar, right? So it's really convenient. And then again, we use a for loop, nested for loop, and we'll call up to create a graph as such by averaging all the albedo values per pixel per day and putting it over time to get one of these, and I'll superpose them with cloud coverage data to actually see a trend.
Now we use superposed epoch analysis so we can represent our data into graphs. For most of the data, the percent cloud coverage and the average albedo are not represented because they're dimensionless, meaning that we're not able to see them on a graph. Also, because we're not able to see them on a graph, we don't have any trends or correlations. So using epoch analysis, we're able to isolate the periodicity and correlations, which will allow us to see the relationship between the different albedos and hurricanes.
So our results were concurrent with the existing research in that we found a strong correlation between albedo and cloud coverage, and then we found that for low-lying clouds specifically, long wave flux and short wave flux were equal, whereas for other types of clouds, these values typically have opposite signs. This begs the question where our study differs. Our high resolution and corruption corrected data allows us to look at spike events from a new perspective, in that albedo values have a higher number for a longer period of time, creating a wider spike compared to those spikes created by the cloud coverage data. Additionally, we can see to the left and right of a major spike event that albedo values seem to spike to a lesser extent around these as well.
To summarize, our goal was to find a relationship between cloud coverage and albedo in the North Atlantic region, and as we hypothesized, there was a relationship between the two. After studying 5 hurricanes, we noticed 2 phenomena. First, the main albedo peak was wider than the main cloud cover peak, and albedo increased before and after the main spikes. As interesting as this is, there's still more to be discovered, and limitations to surpass. For example, we studied low-level clouds. What if we were to consider mid and high-level clouds? Also, what if we were to consider a different region, like the Pacific region, perhaps? In continuation of this project, we could look into disagreements in data, for example, the differences in Earth-Chine albedo and Sirius albedo, which measures albedo from different angles. All of this to say, our findings are just the tip of the iceberg, and there's still a lot to find. We'd like to give a special thanks to our advisor, Andrew Jared, and thank you for listening.